Okay, I guess we're starting. Thanks for coming to hear me talk again. I submitted a topic, of course, and then I start working on my slides. And as I worked on the slides, I start to change the topic. So hopefully, what I talk about today seems familiar to the abstract, so you're not too, too misled. But my coworker Hannah is upstairs talking about context for data structures. She's a great speaker. You could still have time to catch her if you. So my final topic today is integer portability and safety related systems. I, initially planned to just mostly complain about MISRA, but as I started working on the slides and sort of exploring some of the portability issues, I started to realize, just really how problematic portability is in C and C++. So I went into that a little bit more detail. But these topics of integers, portability, safety, they're all, will all be covered here. So just to start with kind of the definitions, I've done security for some years. 2003, I started working in CERT at the SEI. And a few years ago, I joined Woven by Toyota, and my focus shifted a bit to safety, and started finally to understand a little bit more what functional safety meant. And it's not exactly what I thought it was before going to Woven and thinking about safety. So functional safety is the systematic process used to ensure that failures don't occur. So you can have faults in code, passive flaws, and maybe the fault is never executed, and that's the end of it. The fault could execute and cause an error to occur. And faults are, they're not great things. Errors are not great things. But in safety critical systems, they are tolerated, and they're accounted for, right? So probably if you don't consider them and account for them, you probably don't have a safe system. You just can't kind of go with the assumption that, yes, it's all correct. So the thing that's not acceptable is failure, right? And so you have to make sure that if you have a functional unit, that it's able to perform its function. And the obvious examples are, hey, we have a braking system, right? And there might be an error in the braking system, but that error cannot lead to a failure, right? Because a failure could lead to, injury or harm coming to people, or property. So that's a kind of overview of functional safety. Portability. I've said for years that the word portability is ambiguous, and so I tried to nail it down a little bit more. I originally thought I would have more kinds of portability than I ended up with, but I really here I have two, maybe three. So software, and these are my own definitions. I didn't steal this from anywhere, but software portability I've described as a design objective for source code to be easily made to run on different platforms. So that's the broad concept, right? You want, God, to quote from Java, write once, run it everywhere. So I've broken that into two separate things, though. Build time portability, which is, does the code I'm writing use only features of the language and library that are guaranteed to exist and have the same behavior on the target platform? So very simply, is this code going to compile and link? And sometimes the code not compiling and linking is better than the other alternative. So the separate aspect of this is runtime portability, which is, does the language compiler or library function have the same behavior on the target platform? Will it have the same runtime behavior? So that's probably definitions for code that you're writing. There's other flavors of portability. Like in class the other day, I see some of my students in the audience. I was talking about C being a more portable language than C++. And what I meant by that type of portability is that, there's more compilers on more types of hardware that run C than run C++. So if you have a C program, theoretically you can move that further, to more different types of systems. So that's a third type of portability that I'm not focused on here right now. But the word portability is, it's sort of unfortunate because you say portability, people think they know what you mean by that term, but there's a chance they are thinking something else. It's not a very precise term. So in terms of the C standard, it talks about implementations, and there's a concept of conforming programs and strictly conforming programs. And so conforming programs can depend on non-portable features of a conforming, compiler implementation. So that's mostly, say, implementation-defined behaviors, things like different implementations having different sized integers. And there's a concept of strictly conforming, which is a program that only uses features of the language and library that are specified by the international standard that are then maximally portable among conforming, compiler implementations and don't, for example, depend on implementation-defined behavior. And the reason that the C standard defines this term strictly conforming is to sort of, to better define what conforming means and to kind of make the point that this is not what anyone is trying to achieve, right? So this is kind of a carve-out, right? People are not meant to try to write strictly conforming programs, right? So no real-world programs are strictly conforming. It shouldn't be your goal to try to write a strictly conforming program, and a strictly conforming program is worse, not better than a conforming program, right? And so the problem is there's quite a lot of latitude in the C standard, just to keep on the topic of integers, right? The constraints are minimum ranges for various types and that smaller types are not larger than larger types, right? So a conforming implementation could be that char, short, int, long are all 64 bits. Completely conforming implementation. So now on such an implementation, you have sort of interesting characteristics like you can't convert an unsigned char to signed long without testing the range, right? Because it's possibility that unsigned char won't be representable as signed long. So in a strictly conforming program, you would have to add extra tests before doing that, right? But that's idiotic. There is no implementation now or ever that will make those choices, right? So really writing strictly conforming program is a non-starter. Yeah, I mean, the joke is, right, people have always said C is a portable assembly, right? And that's wrong really on both counts. So A, it's not portable, and B, it does have semantics, and increasingly it has semantics, and the semantics tend to throw people off because they like to think of it as just generating instructions and the hardware will do whatever it does with the instructions. But increasingly because of trying to improve optimizations, things like alias analysis, pointer provenance. Increasingly there's an abstract model, and the conceptualizing it using a hardware model is more and more problematic. Okay, I'm on slide 3 or something. So portability is not safety. So if you have code which doesn't build, then it's safe but not portable, right? So the most secure code you can ever write, you put the code on the machine, you turn the machine off, you put it in a bag with some rocks, and you chuck it in the lake, okay? That software is not going to harm anyone. I mean, maybe someone will catch their anchor on it, but that's a hardware issue. So in this case, doesn't build. There's no runtime behavior to consider. So if it builds and it has the same runtime behavior, that could be considered safe and portable, right? You've tested this code, you've established the safety of it. If it has the same behavior on another platform, it should also be safe. Maybe the most dangerous square here is that it does build, but it has different runtime behavior, right? So that code is portable, but unsafe. And probably the best example of that is the setUID function in POSIX. The setUID function is available for all flavors of Unix and Linux, but because it's been around the longest, but on every platform, it behaves quite differently. And so if you just port that code over, it'll look fine, but there's a good chance that you've messed up your permission model, and any flaw in the permission model is immediately a vulnerability, right? You don't need to even combine that with any other input validation error or anything. So let's talk about MISRA and AUTOSAR standards. I'm a member now of both the MISRA C committee and the MISRA C working group and the MISRA C++ working group. And I think I announced this 1 year ago at this meeting, but I'm also the convener of the C standards committee. And so, yeah, it's kind of interesting being involved in these various activities. So MISRA C, and I've listed 2023 here because this is how it looks in 2023, but this has been there since, when did MISRA begin? 2004, 2012. It's been there through all the versions. There's a directive that says type defs to indicate sign and signedness should be used in place of basic numerical types. Char, short, int, long, 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 float, double, long, double should not be used. So you're not allowed to have these kind of words, these type names appear in your code. So you have to use type defs, right? So the MISRA C 2023, just newly minted version of MISRA, gives examples like, oh, you should have a type def for short, which is int 16t, or a type def for int, which is int 32t, right? And so that's all good and fine, but what about 16-bit integers, right? If you're on a 16-bit integer and you're using this int 32t type in lieu of int, now you have mismatches with anything that's based on int. Same thing with long, right? It's very common for implementation models to have a 32-bit long, not a 64-bit long, perfectly allowed by the standard. Long has to be at least 32 bits. Int has to be at least 16 bits. C is has a long tooth, right? It was around when 16-bit processors were the norm. So this is this is sad. This is I keep feeling like this is something that kind of engineer out of a third-rate college in the UK, did on his first job and then thought it was very clever and put it into the MISRA standard, 5 or 10 years later without really thinking about it again and how, how harmful it really was. And because this started out in MISRA C, it sort of propagated through all the MISRA standards. So now MISRA C does highlight the issue that it might not be desirable to apply this guideline when interfacing with standard library code, right? And so there the issue is quite clear. You have a function that takes an int, you pass an int 32t, well, okay, maybe it's the same size, maybe it's not. If you're on a 16-bit implementation, that's a different size. So now you're passing too large of a value that can truncate. So suddenly in all your API calls, you have to inject range tests, but not in a portable way. So they're forcing you by these rules to write really shit code. MISRA C++ 2008 adopted this rule, but made it advisory and not required. So that's nice, because the first thing you do is you disapply it, and you never think about it again. And I recommend that at the end, but I'll recommend it now as well. Yeah, and you know, these MISRA working groups, there's some very strong conceits there, right? I mean, the initial sort of conceit is, we're smarter than the C++ and C committees, right? Those committees have made all these mistakes. We're going to clean it up, right? And the fact is that they're not. They're not smarter than the members of the committee by a long way. And then the second conceit is, let's invent a new rule from whole cloth. Let's make it required, okay? No, right? Make it advisory, collect some user data, right? And then determine if it's been, you know, if it's been successful or it's been a failure, right? And if it's been successful, then think about making it required, right? But don't start with it like that. Don't inflict, well, it's in the name, don't inflict that misery on everyone without, you know, validating it with the community. We're not taping this, right? So MISRA C++ 2008 gave way to AUTOSAR. AUTOSAR made the unfortunate leap to make this required, right? So my organization, we are following AUTOSAR. We're using C++ 14. We have to follow this. So it's quite unfortunate. So here, again, it's basically the same rule. Char, int, short, long should not be used. I assume they meant to include long there as well. They didn't specify that type. But it raises interesting questions, right? So did they fail to specify that because they forgot, they forgot to say that and they meant to? Or, and so you have to decide, because the whole rule is dumb, right? And so you have to decide, do they want it to be more dumb? Should I be even dumber with this than they've specifically said, right? So it's a hard call, right? Or do you follow very precisely whatever they've said here, which in this case, long's okay, apparently, which is strange. And then there's this kind of fun joke, right? Because what a lot of developers do when they first try to convert their code to MISRA is they'll do a global change of int to int32t. And so we have this example of, reinterpret cast turning into int32 interpret cast, right? So that's just kind of common fallout from this sort of these sort of requirements. MISRA C++ 2023, very freshly minted. Again, the same rule. This is an advisory rule, so step one, disapply it. Don't look at it again. So this rule applies to names, again, char, short, long, signed, unsigned. So here it says the keywords, right? So that would disallow long. Kind of interesting here is how float and double fell off the list, right? Which it was there in MISRA C. So, if this made sense, you would think the rules in C and C++ would be the same, but they're not, right? And also, as you go through the documents, you see the rationale for these rules just moves all over the place, right? They can't really, And I've been in meetings where I've attacked this and just listened to them go from one reason this rule exists to another, looking for something that'll stick to the wall and never finding it. So they want you to use exact width integer types. They don't know that that's what they're called, but they are called exact width integer types. Int n underbar t is assigned integer type with n and no padding bits. So for example, int 8t denotes assigned integer type with an exact width of 8 bits. The unsigned are the same, except with the U before it. So UN24T would designate an unsigned type with a width of exactly 24 bits. And from a portability perspective, these types are not great, I mean, for starters, they're optional, right? So if you're on a platform that doesn't have a 24-bit register, then you don't have a 24-bit type, right? So it's hard to require it if it's not there. But if an implementation does have that size, then it is required to define the alias, the type alias. We have also minimum width integer types. So int least nt is a signed integer type with a width of at least n. So there's no signed integer type with lesser size that has that specified width. Int least 32t would be a signed integer type with a width of at least 32 bits. Same for unsigned. There's no unsigned type with a width less than the specified width. So if you have a type like uint least 16t, it's really indistinguishable from unsigned short, right? They're both just the same. They're both saying we're guaranteeing a minimum width of 16 bits, but we're not saying it's 16 bits, so it's 16 bits or larger. So unsigned short and uint least 16t are the same types. A big question you can ask is, does MISRA allow the use of these type defs? And you have to give that some thought. It's sort of up to interpretation, right? I guess that probably the three standards you might interpret different, what it says. The MISRA C standard says, really all it says is you have to have an alias and it has to have a number. Really, in the name of the alias, right? So these would qualify under MISRA C. But when you get up to MISRA C++, where they're talking about the rationale being knowing the exact size of the object, now you kind of wonder, because with these types, you don't know the exact size, right? They're at least that size. They could be larger. Yeah?
Do they mention anything related to things like size D?
No. I have a slide on that.
And a related question to exact width types, but maybe this is for your session tomorrow on Rust. Do you happen to make that connection with how integer types are defined in Rust? Because they lean on the exact width.
Oh, I didn't. Yeah, I'm not a strong Rust programmer. So if you're coming to my session later on, and you're looking for strong defensive Rust, you're probably not going to get one. Yeah. I'm not trying to attack Rust, but I'm not a strong Rust programmer, so I probably can't offer a strong defense of the language. But yeah, I'll get more to the pointer diff t stuff and size t. And then finally, there's fastest minimum width, which is the fastest integer with a width of at least n. So again, you don't exactly know what the size of these are. It is common for, if you have int fast 16t, it would be common for that to be a 32-bit integer, for example, not be the size that you see. Okay, so this one slide is the main problem I have with requiring the use of exact width types and not standard types. So int is sort of a linchpin type for C and C++. It's the natural width suggested by the architecture. So, on a 16-bit architecture, it's 16 bits. On a 32-bit architecture, it's 32 bits. On a 64-bit architecture, it's still 32 bits for some reason. So small types are promoted to int as part of the integer promotions, right? So the type int shows up in the definition of the language, right? I mean, outside just saying here's a type that you can use. There's behavior, integer promotions, which forces objects into this size type. So the standard integer types have minimum ranges, so each type provides at least as much storage as those preceding it. And so if you're sticking with the standard types, you know the relationships of these types. You know that short is always at least as large as char, and int is always at least as large as short. So you know that you can safely convert a char to a short, and you can safely convert a short to an int, you can always convert any integer to a larger, a wider type of the same signedness. That is always a safe conversion. You don't need to be concerned about looking at the value range. But what we've established up here, right, is that you are going to produce ints in your code, right? You're also going to, yeah. So you're going to have expressions which are going to be an int. And then the question is, let's say you can't write your code, you're following MISRA, you can't write your code to use the word int anywhere. So you have to pick a type, and most people pick int32t. And so now the question is that int32t the same size as the int on your system? And the answer is you don't know. Maybe it's the same size, maybe it's larger. Okay, so you have an int24t. Where does that fit in? It could be larger than an int, it could be smaller than an int, right? So you don't even know, can it be converted to int without possible loss of data? You're now sort of making everything more vague and less well-defined. And this is not in the interest of safety or security. So requiring use of these exact width types, and I mean, I'll just go a step further, right? If you're a normal C or C++ programmer and you look at some MISRA code, the first thing you think is, what the fuck is with all these exact width types, right? Because they're not used the way any normal C program would use. It instantly looks very strange, and it's because it is strange. It's an absurd way to use these types, and there's now safety critical systems all over the world which have sort of been forced to adopt this, and the reason people do adopt this is it's easier to give in to the will of MISRA than it is to fight this, especially AUTOSAR, where it's a required rule and you can't simply disapply it. So I'm trying to remember why I have this slide here. It's a fun slide. I guess I'll talk about it and then maybe I'll remember why I included it here. So we have an interesting example with uint16t where we assign it a maximum value, and then we go ahead and say multiply a times b. And so what happens here? Let's say we have an architecture where int is 32 bits. So this 16-bit type is undergo integer promotion, so it's going to be converted to signed int. So both a and b will be converted to signed int by 0 extending these unsigned values. And when we do the multiply, it turns out this case where you've got the largest possible value multiply itself will overflow the signed int and set the signed bit. It's only this one edge case. But it allows for the possibility of producing a negative value with undefined behavior. So on GCC, if you multiply a times b, you get a negative number. That's not horribly shocking. But then also, this test here will tell you that that number is not negative, right? Which that looks exactly like UB, like really sort of odd statements. On Clang, it'll produce this same result, but it will tell you it's positive, right? So now different compilers give you different results, which again is sort of indicative of UB. Okay, so here's where it gets kind of highlights again the problem with these exact width types. So we have int16t. We have two values, j and k. And we have int32t and integer L. And here, this is MISRA compliant code, right? I'm not using short or int or long. I'm trying to write code that, my tools aren't going to complain about. And so the question here is the left-hand side, does the left-hand side of this equality operation have the same type as the right-hand side? So raise your hand if you think the left and right-hand side have the same type. 1, 2, 3, 4, 5, 6, 6. Okay. How many people think they have different types? Okay. More on the different type. Maybe the people who don't want to commit are the majority. I think the answer here is it depends. So let's first look at a 16-bit implementation where we have 16-bit int. So here, these two values undergo integer promotions, right? But on this platform, 16t is basically an alias. It will be an alias for int, right? It'll say type def int 16. So this addition takes place as a 16-bit operation. Afterwards, it's going to be compared to L, which is a 32-bit value, right? So now we have to apply the usual arithmetic conversions to balance this to a common type, which is going to be, int 32, or on this platform, probably a long type, right? So the answer on 16-bit implementations is no. We do not have the same type on either side of that inequality operator. Now, on a 32-bit implementation, if we look at this, we're going to use this int 16t type as a R value, and because it's smaller than an int on this platform, it's got to undergo integer promotions. So this is going to be promoted to 32 bits. K is going to be promoted to 32 bits. This addition is going to take place as a 32-bit value. Afterwards, it's going to be compared to what's already a 32-bit value on the other side, right? So here you have a real difference in behavior from a 16-bit architecture to a 32-bit architecture, and many of the reasoning varies, but frequently the reasoning in the MISRA standards is, we want to know what size things are. We want the code to be portable, right? This has become much less portable code by forcing the use of exact width types, right? So if I were to write this in violation of the MISRA standard and just use the standard types, so here I have short and the int L, you know that short is going to be promoted to int, right? It's quite clear on any architecture it's going to be promoted, even if it has the same representation. So J and K are promoted to the size of int, and this comparison, the type of the objects on either side of this comparison are always the same, right? So we know more about this code than we knew about the other code. So to me, this is clear, better code. And, it's still, unfortunately, still not portable, right? Which kind of starts to go to the rest of my slides, which is, should portability be a goal? It's strict conforming programs are sort of a, fantasy. But I'll kind of keep going from here. So something we could do is make things all the same type. So this is good. In general, this is a good rule of thumb, right? Try not to have mixed types in a single expression. Try to have all the same type. Now you don't have to worry as much about conversions. So here, sum in comparison of both 32-bit operations, unless int happens to be wider, which is allowed for by the standard, but I don't know of any implementations that have int wider than 32 bits. So it's not very common. So this code is, not too bad. You can use the greatest width integers. So greatest width integers have had a lot of problems lately. Right? Originally they were meant to be the greatest width of the standard types and the extended types, but because some mistakes were made and these types were used in APIs, right, it suddenly became an issue that, well, hey, if I introduce a 128-bit extended type, now my int max size has to increase, which means now I've broken my ABI on all those function calls, right? So what compilers did in response to this was did not introduce extended types at all, ever, right? And so just the existence of this type broke up a basic language mechanism for extending, the use of integer types into language. So in C23, we fix that by saying it's the largest type of the standard types. So extended types can be larger, bit precise types can be larger, and the so this is okay. The only thing wrong with int max t now is that the name is a lie. Right? It is quite certainly not the largest integer type you can create on your system. So this is sort of portable. It's not completely portable, right? Because int max t can have different sizes on different platforms, meaning you'll wrap around or overflow at different points, right? So it's not the same runtime behavior. And of course, using the grace with integer types for everything can be inefficient. So not really an approach I think anyone would recommend doing it like this. So really, as we looked at each of those solutions, none of them were entirely portable. So the value at which addition overflows, which is undefined behavior, is always implementation defined. So I came up with this quote that runtime portability is the infantile fantasy of MISRA working groups and software neophytes. And I asked people if that was too harsh of a statement, and they said, "No, leave it in. It's funny." So I put, Groucho Marx. If you find it hard to laugh at yourself, I'll be happy to do it for you. Okay, so let's try to again keep making this code portable. Right? It's just 3 lines, pretty common stuff, right? You're going to have 1,000 kind of cases like this throughout your code base. So here I used again. I wrote some. This is MISRA compliant code, right? I don't use char, int, or any standard integer type. I say uint 16t. And uint 16t, we know the exact width, so we know the exact range. And so quite purposely here, I didn't use a constant from limits.h. I used, integer literal. And here we're just making sure that the operation's not going to wrap around. If it does, we treat it as an error condition. And so this is, so what we've done here is we've assumed that our int is 16-bit for maximum portability, right? And this is kind of how you get portability, right? Is you look for the lowest common denominator across all the implementations you might support, and you limit yourself to that. So I use the example of strict FP in Java, which is sort of the same thing, right? If you want consistent floating point behavior, the way you get it is you say, give me the worst possible floating point behavior, and then it's consistent, right? So you either get the best behavior or you get consistent portable behavior, right? It's an either-or type of choice. So this example is going for the consistent behavior, at the cost of having not as good, having overflow occur much easier, having code need to fail when really it could succeed, right? Which is not ideal. So strictly conforming code, kind of said this in the beginning, it's defined. It's defined by C standard to identify an unachievable and undesirable state. So the typical discipline in C, and C++ guys might not admit to this, but it's the same. It's as far as integers are concerned, they're the same language. There's not any significant difference here. And so in C, the usual discipline is you build your code to a reference platform. You say, we're going to run on this platform, and you make sure it works. And then what I like to do is anytime I have a dependency on implementation defined behavior, for example, I'm assuming I've got a 32-bit int, so I can represent the full range of values, I'll write a static assertion, and I'll say, the width of int is at least 32 bits. And now if someone down the road tries to port that to a 16-bit processor to save 8 cents per unit, they'll get a fatal diagnostic to prevent the compilation. They can look at the code, and now they can think about the per unit cost of the processor versus the cost of porting the software. And frequently people make the decision to port the software. It's more cost effective than paying, if you got 1 million units, right, that 8 cents adds up. So it's important to document these assumptions, document the use of implementation-defined behaviors. So I started working on a rule for us to follow to support this type of portability where you could place a static assertion either before or after the statement that assumes a non-portable integer width, or at the declaration of that integer, just to cut down maybe on the number of locations. This is a weird trade-off, right? You want the static assertion to be in proximity to the issue, so if the thing triggers, the developer can see what the problem is. But you don't want to have like 1 billion of these static assertions, right? I mean, at one extreme, you would put all your static assertions in a header file that you would include everywhere, and that would be a kind of a configuration file, right, that defines all the assumptions you've made throughout your code base in one place. But then it's hard to find where those things have been violated or where those assumptions have been made. So, just a quick example down here. We're adding this base value, which is a large number, to 512. On a 32-bit, on an implementation of 32-bit integers, no problem. On a 16-bit integer, this will overflow, right? So you can introduce a static assertion here that says, if put the math in here to see whether wraparound is possible, because this is an unsigned case. So this is fine. This will work. Or the other way you can do this is just document your assumption about the size of the types, right? So either of these will trigger a compilation failure on a 16-bit platform. Okay, so integer type selection. When you're programming and you've got to pick an integer type, it's largely driven by the need to match APIs, right? The first thing I look at is I've got to call this API, what sort of types of arguments am I going to pass to that? And then I try to do things in that type so that I don't have to worry about the conversion to, when I call the function. And so there's I think I have this here, but there's there's a corollary to this, which is, API design is really important, right? Because if you get the wrong type in your API, here I'll make a bunch of other people mad. Let's say, for example, you use an S-size T type, right, which is an abomination. That is going to destroy the rest of your code, right? Because now everywhere else you have to think, do I use the correct size T type to represent a size, or do I use this abomination of a type S-size T to represent a size? So if the API accepts an int parameter and you pass an int32, how will your code behave if that int is implemented is not defined to be 32 bits. For example, it's small or 16-bit type. So having this different type now means you have to add these tests if the value's out of range, and if it's out of range, okay, how do you handle that? Is it going to trigger a failure? So it's quite messy, and it's for no reason. It's for poor reasons. Converting between implementation defined types and exact width types is difficult and error prone. And there's my corollary about the API design. So matching APIs is somewhat feasible for user-defined code, right? Your library calls can all take int32t, and your application code can pass it. It's more problematic, of course, when interacting with standard library code, where they did just the normal thing of using standard types and not this absurd thing of specifying everything using exact width types, which again would create ABI issues, right? If the types change per platform. So matching API. So say you want to use strcomp, and strcomp returns an int, okay? So you might write this code int I equals strcomp, and then it gets flagged by the tool because you used the int type, the forbidden standard integer type. It seems silly, right? But it's reality. So what developers do is they'll say, oh, I'll use auto here, right? And so now catching an int return value from a function with an auto variable frequently doesn't trigger a violation for the static analysis tools. So it's a good way to violate the rule without getting caught. So what are we doing now? We're writing bad code to violate a bad rule to avoid detection, right? That's really happening. And, so how is this rule helping us again? They sent us down this, this is how you wind up in hell. You start following these good intentions. There's a quote there, right?
It's auto from AUTOSAR.
Yeah, auto for AUTOSAR. Thank you. Okay, so how do you use types? I mean, you all know. I mean, that's what makes this whole thing silly. Exactly types are used when representing fixed width registers or, say, fields in a network protocol or file formats when, say, you just want to read it into a struct and you want everything to show up in the right place. That's how we use these types. We don't use them for loop counters. Minimum within types can be portably used to ensure you get the smallest type of some size. Fastest minimum width types can be guarantee a minimum range, but optimized for performance over storage. And then, your question, size T and pointer diff T, really all these MISRA guidelines are completely silent on these types. Okay, if you think about MISRA C, probably no, you can't use these. Why not? They don't have numbers in the names. That's like the MISRA C requirement. You have to have an alias with a number in it, so these don't. And then you look at MISRA C++ and AUTOSAR, they talk about, knowing what the size is, right? And if you use these types, you don't know what the size is. Size T is 32-bit unsigned or 64-bit unsigned. Pointer diff T is 32-bit signed or 64-bit signed. Now, what happens in practice is analyzer vendors take liberties, right? They're like, if there's a little bit of vagueness in the MISRA standards, they try to make it sensible, right? And so what most analyzer vendors would do is not diagnose these, right? So if they strictly follow the rules, they probably would, but they kind of take a little bit of leeway to take the edge off the stupidity, right? And thank you, analyzer vendors, for doing that for us. So you could, I had someone say, well, hey, you could reproduce this by, creating an alias type, which depends on, right? So now, again, this is pretty bad, right? You're sort of reinventing a mechanism just to, comply with this rule when it's better and safer just to use the existing mechanism. So I'm going pretty fast here, actually. So roadmap and recommendations. In MISRA C++ 2023, this rule has been downgraded to advisory. So the first thing I did was disapply it. The second thing I did was went to the MISRA committee and said, you need to get rid of this. So the C++ committee is open to the idea, right? Because they've already recognized the issues with this when they moved it from required to advisory. They want me to provide them with a replacement rule that captures places where you should use exact width types and don't, and then they'll be open to eliminating this. So, hopefully I'll find the time to do that. The MISRA C committee noted my objection to the rule, right, which is how you say fuck off in British, as far as I can tell. Yeah. So that's kind of the status here. If you can disapply this rule, disapply it with prejudice. If you have to use it, I don't know. I mean, we follow this because we're using AUTOSAR and it's a required rule. So yeah, disapply this rule. Similar rules, try to use static assertions to ensure integer sizes meet your minimum requirements. And use exact width types for the kind of things they're meant to use. Yeah, and this is all since I've 10 minutes left, the basis for this kind of stuff is when you sit in MISRA, you think about C developers, and you think, do I think a C developer will know this, or do I think a C developer might not know this, right? And so if you think a C developer might not know this, you'll create a rule to say you can't do that. But now you've created a burden that the C developer needs to know about the rule and how to apply the rule and all that extra stuff. And so what they're getting at here is that we don't, I think the very specific cases, we don't think C programmers know that int might be 16 bits on some architectures, right? But to me, it's easier to teach them that it could be 16 bits than it is to explain the rules, explain the integer promotions, explain all the complications that might come about by mixing exact width types in with, smaller integer types which promote to int. So, this trying to think about what developers know and don't know is sort of problematic, and it's especially problematic because it's not data based. It's just people making stuff up. Their feelings about what people might know. So anyway, I have time for some questions. Yeah, thank you.
So it's sort of a tangent, I suppose, but would it be practical to just throw the entire rulebook out and ignore it and still pass? Because this is in order to comply with regulation, right? This is a shortcut for regulation.
Yeah, I would say that it's about liability, right? And so what's happened, say, there's been, accidents, and people have gone to court, and they've said, we followed MISRA, and MISRA is the best practice, and those organizations were not found liable for, accidents that have occurred. And so people, I think, follow MISRA because it's been successfully used in court cases to avoid liability, right? So I think that's the top driver. Back when I worked for NCC Group, I had proposed giving a talk called, MISRA C, why aren't more people dead? And they were really into that because that's their business model, right? They want to sell, code inspections and all that type of stuff. And I mean, to answer my own question, I think it's because the diligence of engineers who make MISRA work. I don't think MISRA is helping them. In some ways maybe it is, but in a lot of ways it needs significant improvement. Any other questions? No? Okay. Yeah, sir.
I have a question not necessarily on MISRA.
We got some time, yeah.
So I'm more specifically interested in the portability angle and how you started sort of presenting challenges and misconceptions around portability. Aren't we maybe too concerned with portability? And I keep, when you were talking about this, I keep remembering some of the ideas that Mike Acton will push out, I think, years ago at CPPCon on we should focus on knowing your target architecture and not try to get common denominator solutions.
Right.
And find those sort of generic things that work across the board. And of course, he framed it in the context of performance, not safety. But the idea of portability usually gets you to crappier code rather than you knowing your exact target platform and knowing the details of that architecture and writing the actual code that is suited for that target platform.
Yeah, I think that's true.
So maybe this obsession with portability leads us to bad places.
Right. So security and safety are independent quality attributes from portability, right? And so safety and security need to be certified per implementation for specific set of hardware. So, you know, it's nice to have some level of portability. You don't want to unnecessarily introduce code that's not portable, right? And so, like, I would be very hesitant to assume pointers can be stored in int, right? I mean, that runs on a bunch of 32-bit systems, but we all know what happens when you get 64-bit systems with that. So I would avoid that kind of thing. Something I advise people in my class is don't use small types for just one-off variables. So don't have a short used, you know, as the smallest type int or unsigned int. And by using int or unsigned int, you eliminate integer promotions, which has implementation-defined behavior, right? It'll convert to either signed or unsigned int depending on the sizes of the integers. So now, on the other hand, if you have an array of 10,000 elements of values 0 to 255, yeah, use an unsigned char because there's a significant memory cost there. And then, you know, you have to be a little more careful in how you code that to make sure that it's going to work on whatever platforms you port that to, or define your, you know, constraints, your implementations about what implementation-defined behavior you have. So, yeah, I think it's too driven by portability, and I definitely think portability and security are independent concerns. Yeah.
I have a sort of follow-up. Does that not help Robert's case in this? Is if you know your target platform, you should definitely not over-constrain the size of your basic types?
Yeah.
Right? Yeah, okay.
Yeah.
I wasn't opposing it.
Yeah, I think we were all in agreement.
Yeah.
Yeah, okay.
Any other questions? Yes, sir. Oh. Well, this was all kind of the same question, and it was basically, do we overemphasize, portability at the loss of sort of other quality attributes like performance, and I think, frequently we do. Yeah, so you heard my answer. Okay, any other questions? I feel bad for this guy, just showed up.
Yeah, sorry about that.
He's not going to get too much. Anything? If not, we can end a couple minutes early, and you can enjoy a hot beverage in the other room. Okay, thank you, everyone.